Hello again, this is Josh. Now that we have the CGS program understood how the PV system operates, we can look at the system options and the potential savings that we've come up with based upon your historical consumption and other factors. Now we take a value engineering approach to system design, and we're looking to produce two potential options based upon a number of value engineering considerations, including your Helco bill, your available roof layout options, the types of modules that would be available, high efficiency versus max efficiency, and various project costs that may be considered in the process. So the first option we call the max value option, and this is one that if you're using the state of Hawaii financing program or some other means of financing, given those value engineering factors, this system is going to produce the most net savings over and above your debt service. It's also, if you're purchasing the system with money that you have saved up, it's going to provide you the quickest payback on that investment. So that's why we call it the max value option. Option two is max savings, and this relates back to how the CGS program is structured and maximizing the total amount of savings that you can get out of the CGS program with a system on your roof based upon limitations of roof space and the types of modules that can be used, as well as your historical consumption based upon the Helco information you provided. These two options in some instances may be quite similar, and some may be very different. It just kind of depends on the factors that go into it. We'll take a look at these two sample options here. Now again, this was for a household that consumes about $270 a month in electricity plus their customer charge. So this system, the max value, we use the LG 295 module. Again, great price point, and we get a lot out of the roof space that we use. And we were able to put 22 of them. As we can see down here in the layout, there were certain restrictions on utilization of this roof, and using the roof on the north side ended up being counterproductive from a system efficiency standpoint. So it actually decreased the savings on financing, putting modules over here. So we just focused on the southeast and southwest facing roof. These two here are the two inverter options. If they wanted to go with the end-phase option, this would be the inverter we'd use, and SolarEdge, that would be the inverter we use. Now this is a typical average home using about 25% of their energy during the daytime and 75% during the non-solar production window. So the two savings from these systems, you can see the self-supply estimate for the max value is about $800, and the grid supply credits just under $1,000. Again, more than 2/3 of the system is generally going to be exported to the grid, but you're only getting 15 cents per kilowatt hour on that. So that's why the grid supply credits are not going to necessarily be a lot more than the self-supply, even though only 25% of the PV system's energy is going directly to the household during the daytime. So total bill savings on average per year were just under $1,800 under the max value option. And under the max savings, the system size was increased slightly, though the module count remained the same, and that's because we use the LG 330. So we're getting more power out of the same roof area as we did with option one. Slight change in the inverters that would be used for that because of the type of module that's being used. And we can see that the system increases in savings from just under $1,800 to now about $1,900. So it is a bump in savings. Anything beyond the size of this system here represents a project that would cost more but not increase your actual savings by any significant amount. As we can see, this additional 0.8 kilowatts increased the savings by about $140. If you were to go up to 23 or 24 modules, we started putting modules on the north roof over here, you'd start seeing savings of maybe $5 per added module, which is much, much less than what you need to see from a return on investment standpoint to make it worthwhile. Important note here, because it's assumed that this is 25% daytime consumption, that's how your savings are determined. If your household used more than 25%, say you ran your dishwasher during the daytime, or you dry your clothes during the daytime, or you moved your water heater so it heats up during the middle of the day, These are all things that can increase this 25% factor and will increase your overall savings by sending more of the electricity directly to your household, which saves you money at the retail rate, which is about twice the grid supply rate, and it'll take away from the amount of credits that are going out to the grid. So you gain an additional 15 cents, or more like 16 cents per kilowatt hour for every additional kilowatt hour that you can move due to the daytime. So if it's not something you've done already, it's something that you could consider in order to increase further the amount of total savings that you're going to get from your PV system. This is more of like a baseline. Usually every home consumes 25% or more of its electricity during the daytime. So this is just a good baseline savings to represent that. On the layouts, there's just a couple of minor notes down here. These are obviously the PV modules. This is a hindrance, which in this case is a solar hot water system. The red lines here represent conduit runs that can either be done through the attic, on top of the roof, or drop down and run along top of the eaves, depending on your preferences and what's possible on site. And the little green boxes here just represent the solar edge inverter or end-phase AC circuit panel and the AC system disconnect required for the utility that would be installed near the meter, typically. So your existing Helco meter, you can anticipate having a couple of additional pieces of electrical equipment there, as represented here in the sample layouts. And that's about it. Feel free to reach out with questions.